Hi everyone, welcome back to our discussion of Newton's laws. In the last video we introduced the concepts involving Newton's first law and Newton's third law. Starting in this video we're going to discuss Newton's second law of motion. We're saving Newton's second law for last because this is the law that involves calculations with lots of examples involving those calculations. So first of all, just a reminder, Newton's second law says that when there is a net force acting on an object, that object will undergo an acceleration in accordance with the net force equaling mass times acceleration. And I do want to emphasize that this F in F equals ma means net force. So if there are two equal forces acting on an object, but they're acting in opposite directions, that would be a net force of 0 and the object's not going to accelerate. You know that because if you have opposing forces of equal strength acting on an object, then the object isn't going to accelerate. So again, this is for unbalanced forces, and there could be more than two, could be just one, there could be lots of forces acting on an object that would cause it to accelerate. But the net force is the cause, the acceleration is the effect. The units for force, well, let's see. Units of mass are kilograms, units for acceleration are meters per square second, and I guess after a while people got tired of writing their force units as kilograms times meters per square second, so they came up with the unit newtons to indicate the SI unit for force. It's written out with lowercase newtons, but it's abbreviated with a capital N. So, just to give an idea of about how big a newton is, it's a little bit less than a quarter of a pound. So, a McDonald's quarter pounder would weigh a little bit over a newton. And again, with these net forces, we're talking about unbalanced forces. In this case, we're dealing with a situation where the force on the car, at least created by the engine, but manifested through friction between the tires and the road, gives the car a larger force in the forward direction than does friction in the backward direction. So what's the result of this? There's a net force going to the right, and this car is going to accelerate to the right, because these forces are not balanced. So, what about this situation? In this situation, we have an unbalanced force, in that case with friction being a larger force than the force from the car's engine. So in this case, since there is friction, there's a good chance that the car is already moving, so the car is probably going to continue going to the right and slow down. Now, keep in mind that accelerating toward the left is the same thing as slowing down toward the right if we're talking about a positive acceleration toward the left. A negative acceleration means that the acceleration is in what we call the negative direction. But if we're calling the right direction positive, as is usually a sensible thing to do if we know that an object is moving in a certain direction, call that direction positive, then in that case a negative acceleration will be causing the object to slow down if we're calling the initial direction of motion as positive. So just keep in mind signs and stuff like that, and we're going to have more to say about that, especially when we talk about elevator problems in a future discussion. But just a reminder, you know that position and velocity are not the same thing. After all, velocity is the rate at which position changes. But still, for some reason, a lot of people like to confuse velocity and acceleration. They are very much not the same thing. Acceleration tells you the rate at which the velocity changes, just as velocity tells you the rate at which position changes. In other words, acceleration is a rate. Velocity is a rate, but they are not the same type of rate. So just keep that in mind. How about this situation? What would this car or truck, whatever you want to call it, do here? Well, in this case, the forces are balanced, and Newton's second law tells us that if you have unbalanced forces, net force is equal to mass times acceleration. So here the net force is 0, so the acceleration is 0. In fact, you could have just gone back to Newton's first law, say, hey, the forces are balanced, so the object will maintain constant velocity. Now, what about this situation? What kind of motion would you see here? In this situation, the Klingon ship would accelerate off toward the left. Now, that could mean that it's already moving to the right and slowing down, or it could mean that it's moving toward the left and getting faster. So that's really kind of brought to bear with the fact that it's hard to really say any such thing as an absolute velocity or an absolute position when you're in outer space. So, nonetheless, acceleration is meaningful because it can be measured. How about another example? What is going to happen with this helicopter? So, the first thing that you might think is that this helicopter might accelerate in the upward direction, and its overall motion would be going into the upward direction and getting faster. And you are correct that it is going to accelerate in the upward direction. After all, the left-right forces cancel, and the upward force from the lift more than cancels the downward force from the weight, so there will be an acceleration in the upward direction. But the actual motion of the helicopter will be initially moving toward the right and then moving up in a parabolic type of trajectory. So it's going to have an acceleration in that case. So the overall motion is that it's going to kind of be the opposite of a ball that's thrown toward the right. The ball thrown toward the right would initially start off toward the right and fall, but in this case it's going to be going toward the right and accelerate in the upward direction. Now, you've already seen a number of forces with some of these examples. Let's take a look at some commonly occurring forces. And keep in mind that this is not an exhaustive list, but you're not really going to be doing any calculations in this class with forces that are not on this list, at least not in this unit. So first of all, weight. And by weight, I'm talking about W-E-I-G-H-T. Any object that has mass will have weight when placed in a gravitational field. We often call it the gravitational force. And this is something that actually has an equation directly associated with it. Now, if the object is close to the surface of Earth, we even know the rate at which it would accelerate if it was dropped from rest, or even if it was just thrown down or thrown upward in the absence of air resistance. So, if we define down as the positive direction, then the weight vector is going to be a positive force vector in the downward direction. Now, a lot of times we'll call up the positive direction, just depends on the problem. So, we're going to have some more to say about this later, but I'll just give you the equation now. The equation for the weight of an object is given by lowercase w, and it's equal to mg. W equals mg. That's an equation that should definitely be memorized. M is the object's mass, and g is the acceleration due to gravity at that location. Now, unless you're told otherwise, or unless the language of the problem indicates otherwise, the acceleration due to gravity near Earth's surface is what should be used for this, and that is 9.80 meters per square second. So, that does change depending where you are on the planet. Like top of Mount Everest, it's a little bit less, and other places like that, but it's still the same type of idea. The point, though, is that even though your weight is a little bit less at the top of Mount Everest because you're a little farther from the center of Earth, your mass is still the same. In fact, just thinking about our moon, the acceleration due to gravity near the surface of the moon is about 1.6 meters per square second. So your weight would be a lot less on the moon, but your mass would still be the same. And that's something I really want to emphasize again, because if you're on the moon, it's going to be a lot easier to lift a refrigerator above your head. However, it's going to be just as difficult to throw the refrigerator from the surface of the moon as it would be to throw the refrigerator from the surface of Earth. It's just that on the surface of Earth, it's a lot harder to lift it over your head than it is on the surface of the moon. So that's something to keep in mind, because mass tells you how difficult it is to change an object's velocity. If you're trying to throw something, you're trying to change its velocity. So it's hard to throw things that have a high mass, regardless of their weight. Normal force. A normal force is something that an object will experience whenever it's in direct contact with a surface. Typically, something like a tabletop, or a wall, or a ceiling, although of course in those cases it would need to be pressed into the wall or the ceiling by some other force. Typical symbols that are used for normal force are lowercase n, capital N, F sub n, F sub little n. I'm usually going to use lowercase n. I try to avoid using capital N so that people don't confuse that with the units of newtons. Spring force. Whenever an object is compressed into a spring, or extended from a spring, there will be a spring force to try to restore the status quo. The symbol for that is usually F sub s. I don't use F sub e for elastic force very often because F sub e is the symbol for electric force or electrostatic force, something we will discuss later in this course. Friction force. We'll have more to say about this later, but long story short, there's something called a coefficient of friction whenever two bodies are in contact. That coefficient of friction depends on the nature of the materials. Very, very sticky materials or ones that have very strong friction will have a high coefficient of friction. Ones that are very slippery, like relatively wet ice, will have a low coefficient of friction. Symbols used for friction. So first of all, lowercase f is usually used, at least that's what I usually use as the symbol for friction force. But usually I will also apply a subscript of either S or K, depending on whether it's static friction, the objects are not moving yet with respect to each other, or kinetic friction, where one object is sliding across the other, or one surface is sliding across the other. Then there's drag force. It's kind of like friction, but it's different. It happens whenever air resistance is not negligible. We often just call it F sub drag or F sub d, but sometimes people use capital D for it as well. It only occurs when objects are moving through a fluid, and the fluid resistance is significant. Tension occurs whenever an object is held tight by a string or a rope. So we call tension force like F sub T or F sub capital T, and a lot of times also capital T. Just if there's no opportunity for confusion, sometimes I'll use capital T for tension. But keep in mind, in the next unit we're going to be talking about circular motion, and capital T will be used for the period of the motion. Buoyant force. This occurs whenever an object is immersed in a fluid where the weight of the fluid that's displaced by the object is not negligible. So you're not really going to be doing any calculations with it in here, but I do want to make you aware of its existence. And then there's lift force. Whenever an object is moving through a fluid and the object has a particular shape that causes various turbulent patterns to occur in the wake of the object's motion that would cause it to feel a force perpendicular to its direction of motion, that is a lift force. Again, it's not something we will calculate in here, but it's something we will keep in mind. And then there's the electrostatic force. Whenever you're dealing with charged particles, opposites attract, likes repel, then you'll have an electrostatic force. We'll have a lot more to say about this in a future unit. And then there's an applied force, which is your typical, quote, push or pull, and that's often when somebody is literally pushing something with a hand or a finger or something like that. So remember, this is not an exhaustive list. There could potentially be other forces, but we're not really going to be doing calculations with those. In the next video, we're going to use these forces to set up free body diagrams, which will allow us to calculate an object's motion. So until then, I'll see you later, and thank you for watching.